Good morning, everybody. I'd like to divert your attention slightly from the beautiful arthropod fossils that we've just been seeing some fantastic pictures of and talk to you about the environments that these things were living in. So recent and not so recent discoveries of exceptionally preserved biotas from all across the classical early and middle Cambrian have shown us quite a lot about the biological revolutions that are going on. There's admittedly a lot to still be argued about, it would be fair to say, but we've got a fairly good idea of the sorts of creatures that were living in these environments. However, we still know relatively little about the marine environment that they were living in. We've got a general sense from geological data that the Cambrian was generally a warm greenhouse world, and that this warm greenhouse world is still unconstrained in terms of, is still quantitatively relatively unconstrained. How warm, effectively, is warm? So we heard a lot yesterday about the stable oxygen isotope proxy. I don't think I need to introduce it too much here now, just to say that we do have two main sources of stable oxygen isotope data in the lower Paleozoic, well, in the Paleozoic as a whole. We have calcareous brachiopods and we have phosphatic conodonts. And what we can see is that for most of the Paleozoic, actually, where one record starts to break down, the other record takes over, and that we have reasonable coverage throughout most of this time. There is one notable gap, however. That's the 50 million years at the base of the Paleozoic, the Cambrian period. There are no real reliable oxygen isotope data from these classic sources, and there are two reasons for that. Firstly, calcareous brachiopods and calcareous fossils of any kind really over this sort of time have generally been found to be poorly preserved. They've recrystallized, and we don't have reliable oxygen isotope data from the environments in which they lived. And euconodonts, the clade used for this sort of work, don't evolve until the latest Cambrian, earliest Ordovician. So we need to look for an alternative source of this oxygen isotope data if we're going to use this proxy, extend it down right the way to the base of the Phanerozoic. And it's here that I've turned to look at small Shelley fossils. These are, as I'm sure most of you are aware, exactly what they sound like, small Shelley and fossils. And I've turned to the lower Cumley limestone formation of Shropshire as a test case for this, to see if it could actually work. We've chosen this site because it's one of the best dated successions. It's bracketed by bentonite beds above and below. It's dated to 514 to 509 million years. It's got a relatively well-characterized fauna, though again there's still more work to be done on the faunal composition of it. And it has, relatively speaking, limited secondary phosphatization. There are some exceptional exceptions to this, funnily enough. But as a whole, when you find fossils, you find an array of different preservation modes. For instance, we have silicious steinkerns of cap-shaped microfossils. We have sponge spicules preserved in a variety of different ways, including, you notice the one on the top right there is preserved in glauconite, which I find particularly odd. Maybe I shouldn't, I don't know. We also find a lot of primarily phosphatic organisms there. So tomotiids, such as Laprothella, which we have over on this hand side. We have various phosphatic tubes, the phosphatic spines, rhombocorniculum, and for the purposes of this, grouped within small Shelley fossils, though not classically considered as part of that group, we have various phosphatic brachiopods as well. And it's the phosphatic brachiopods and spinose rhombocorniculum that I'm going to focus on for the rest of this talk. Before getting any oxygen isotope data out of these things, it's worth trying to understand where the oxygen isotopes that are in these skeletons have come from. Is it all diagenetic? Is it all biogenic? Or does that actually include some signal of both? Well, we can look at this in a variety of different ways. We can examine the skeletal preservation at the microstructural level, at the ultrastructural level, and we can look at the chemistry of the specimens as well. There are various other techniques I'm working through as part of this as well, which I don't have time to go into here and are sort of still in development, but happy to talk to people about them later on. So to take the brachiopods to start with, phosphatic brachiopods are composed of alternating laminae of effectively more organic matter and compact phosphatic laminae. And we see, crudely speaking, we see those preserved here in comely specimens. In some of these specimens, we'd see effectively blocky phosphate. We don't see this lamination, and it's fairly easy to say those have recrystallized. But at this microstructural level, we do see some seemingly well-preserved specimens. To take a closer look, we find that in the more porous laminae, not the compact ones, but more porous laminae, we have a variety of orthogenic silicate minerals that seem to be sitting around there. We don't see these secondarily phosphatized. We don't see organic matter being secondarily phosphatized in these layers. And when we look at the compact laminae, the dense phosphatic laminae of these brachiopods, we find that we've got apatitic spherules making up the bulk of this structure. These are still on the scale of spherules that you see in modern phosphatic brachiopods. And to have a look at the chemistry, we have effectively relatively clean apatite within the compact laminae, and within the more porous laminae we see evidence of the orthogenic silicate minerals that have formed in there. Now the story for rhombocorniculum is very much the same. We see some that are better preserved at the microstructural level and some that are worse preserved. With this taxon, we're looking at effectively a structure that's could be compared to a group of straws. You pick up a cluster of straws and you have canals separated by thin phosphatic walls. And again, we see that in these specimens here. The thin phosphatic walls are in some cases made up of what look like mosaics of apatite, fairly sheet-like. And in other cases, we can see that we've got seemingly, well, that's turned out very fuzzy on this projection, seemingly much finer nanometer scale, or tens of nanometer scale crystals in the walls themselves, which I can point to those in this specimen running along here. And within the canal spaces, we do sometimes find up to half micron or micron scale secondary crystals. So there is some diagenetic component to some of these specimens. However, we can identify better and worse preserved rhombocorniculum as well. And with the chemistry, we have a very similar feature here. We can see generally clean, seemingly well-preserved apatite in the the body of the skeleton, and with the central lumen, which is effectively hollow, we see orthogenic silicates, and that's pretty much where these secondary minerals are limited to. So that we can say that we can identify a range of preservations of the skeleton of these specimens at microstructural, ultrastructural, and chemical levels, and I'm investigating a few other techniques. So at this point, it'd be worth turning to have a look at the oxygen isotope data that come out of these. And we can see that we have a range of values here. We have on the left-hand side, as you look at it, we have two examples of phosphatic pebble and phosphate hard ground found towards the base of the lower comely limestone. And in the green, we have what we've identified before isotope analysis as better preserved specimens, and in the yellow, what we've identified as poorer preserved specimens, squares are brachiopods, triangles, rhombocorniculum, and the circles are torulella, which are tubes, very thick-walled phosphatic tubes. And we can see that there does seem to be a distinction between the better preserved and worse preserved specimens, and the worse preserved specimens show, as you would expect, lower oxygen isotope values. So can we translate this into any sort of environmental signature? Well, to translate from stable oxygen isotope data into an environmental signature, you have to consider several factors, which have already been widely discussed in a symposium, I think. So we can take an equation of temperature from Lecoyer et al., 2013, and taking a modelled oxygen isotope composition of seawater of about -6, modelled by Jasmine Jaffras in 2007, for oxygen isotope composition of Cambrian seawaters. And the oxygen isotope values of about 14 to 15 per mil of the best preserved brachiopod specimens that we find. We get reconstructed temperatures of between 22 to 28 degrees Celsius. is this reasonable for the environment that we're looking at? Well, Avalonia at this time, which is where these samples come from, was situated at high southern latitudes. So these temperatures are not inconsistent with similar latitudes in warm Cenozoic times, in the early Cretaceous, for instance, as well. And when we take a look at the geological data that we have for paleoclimate at this time, we see very widespread evaporites across Gondwana, across Laurentia, and all around. We have calcretes, which have been interpreted as warm environments, so 22 to 28 degrees Celsius, high southern latitudes, latitudes where we've got evaporites forming, where we have calcrete deposits. I suggest that those are reasonable, plausible temperatures. So to wrap this up, marine environments of the Cambrian explosion have been poorly quantitatively constrained. Well-preserved phosphatic small Shelley fossils are a promising new source of Del 018 paleoenvironmental proxy data, but they have to be worked on a little bit more, I think, at this stage. The first data do support warm, high-latitude temperatures, which are supported by geological data as well. And we can use these to potentially interrogate some of the ecological questions that have accompanied various evolutionary questions about the Cambrian explosion and the Proterozoic-Phanerozoic transition. So, thank you for your time. I'll have to take any questions if there is time.